All right, great. Yeah, so quick introduction to myself as well. My name is Max Schmidt. I'm the customer support manager at Enapter. And generally, when there's questions about the devices or how to integrate them, they come at least past me, and we'll be able to help you out in some sort of way. But first, let's get going into the EL 4.0 deep dive. And we'll start off by first exploring a little bit about our development mindset. So initially, when we started, when the company was started, we wanted to make sure that we can create green hydrogen at the lowest possible cost. In the end, we're competing with well-established industrial processes, but going from a centralized systems to the decentralized green hydrogen generation capabilities, we really thought that this was going to be somewhere where we can make an impact, somewhere where we can really help decarbonize and play a major role in achieving the climate neutrality goals of the whole world. And this is kind of reflected in our product design philosophy as well. We are trying to disrupt the market in a way, and our company principles mirror our design philosophy. We have urgency, simplicity, and transparency. And I think we do a quite good job at being urgent and transparent and trying to make it as simple as possible for people moving forwards. This is something that we're always working on and continuing to show. So basically, this is what we're trying to do. We're trying to replicate the success from solar, and we're trying to do the same thing for this amazing energy carrier with hydrogen. And going back towards our design philosophies, continuous improvement has always been a big part of what we do at Enapter. And I just wanted to point this out a little bit more about the EL 2.1 and how far the system has actually come since we started back in February 2020. So initially, when we came out with the 2.1, it was essentially the CE certified version of the prototypes that we built for the EL 2.0. And throughout its development, we further improved on its integratability, essentially. So the revision A, which is essentially the electrolyzer 2.1 that most of you will know, with the offset purge line, and then the liquid cooled system following, almost a year afterwards, with the DC version hot on heels. Throughout this process, we were always learning and, progressing our internal knowledge and also the knowledge of our system integrators. We were combining these together in order to deploy these systems in better ways. And so we knew that when we wanted to release the 4.0, that we'll be ready for all these possibilities, that we don't take a step backwards in order to keep the functionality consistent. So what did we want to do initially? This was when we kicked it off. I think this was maybe in end of November 2020, we kicked off the design for the EL 4.0. So it's been some time. It's definitely been our longest development process, but I think it's been our most successful as well. So initially, our goals were just to improve the testing capabilities, make it easier to maintain, faster to assemble, in order to leverage the mass producible aspect of it. We wanted the system to be relevant to any ISO, comply to any relevant ISO standards. In this case, it was ISO 22734. And we essentially just wanted the system to be really adaptable. So if you wanted to have a liquid cooled version, you just take out the cooling block and you put a different block in. And that was essentially the design goal. Did it come out in the end as we are pointing out here, with the little boxes all in a row? No, but we did manage to do, I think, a lot better as well. Cheaper, better, lighter, and smaller. This is I think this is the AC version, liquid air cooled for the EL 4.0, and yeah, we're extremely proud to be able to show this off to you guys. It comes available immediately with all the different options that we had explored with the EL 2.1. So we both have the AC/DC versions and the DC/DC versions available, both air-cooled and liquid-cooled. Here you can see the air-cooled versions. Sorry?
No, just someone who had unmuted himself. Okay. Go for it.
And yeah, the units will start being available by July 2022. So what is actually the difference between the two systems? I don't know if you can see this so well. Maybe it's a little bit too small. Do let me know if there is a problem with this. So first of all, weight reduction. That was a big one. Lifting these electrolyzers into the cabinets, if anybody has done this before, it is a two-person job. Now it's still a two-person job, but it's significantly easier as a two-person job. So lifting up the systems, you know, sometimes even over your head, you had to take quite a lot of, you know, you had to bring a lot of strength to it. And now it's going to be much easier lifting them into the cabinets and assembling the systems. The units are smaller. Losing another unit of height for a 19-inch rack is extremely useful. This allows us to actually integrate 7 systems into a single 19-inch standard cabinet, which is like 42 U's inside. And this is huge for us in terms of being able to deploy systems in a more compressed manner. The system is immediately going to be ready for integration into an ISO compliant system. So the ISO compliance that we keep talking about, this is the ISO 22734 for hydrogen generators using water electrolysis. I'll have a little bit more details on this afterwards, but what this means is that it's now getting easier and easier to use our systems and to deploy them directly in installations and industrial applications where these type of standards may be required. Our interfaces have also changed slightly. From having these bulkhead interfaces with the nut and ferrule fittings, we went to these female threaded fittings, which were much more adaptable for our system integrators across the world. So now you're not just stuck with the 1/4-inch piping, but you can choose essentially the output piping that you want to assemble on your systems. Also, we've upgraded some of the system components and added more functionality. So for example, in order to achieve easier compliance with the 4.0, we actually have safety integrated functions inside our system. So our SIL levels are rated. And this allows us to have you know, dependable and clearly defined safety functions, which help us, you know, better transfer the information from what is our responsibility of system safety and what becomes the responsibility of our integrators. We have, if you were here yesterday talking about the safety analysis and the hazard reductions, one of the ones was about managing the oxygen vent and the hydrogen crossover inside the vent. The EL4.0 has a recombiner, which is a type of catalytic converter inside the system. And this helps reduce the crossed over hydrogen in the oxygen stream from the stack. This actually will allow us to run the system at a greater sweep of production rate. And this makes the system even more adaptable. So it's quite easy to imagine, but if you wanted to run, you know, one system or like 3 systems at 60% now, there's very little, there's not that much variability in the production rate that you can achieve. But with the 4.0, you'll be able to have much more fine control about exactly how much hydrogen you're being produced. We also have a hydrogen sensor inside. This sensor is not made for safety. So you will still have to perform the same sort of integrating functions that you previously had to do. So, you know, either with risk reduction from dilution through the room or active hydrogen detection. Kind of depends on your local area and rules and regulations for system safety. But in general, the external safety stays in your responsibility. But and the hydrogen leak detection that we have in our systems is basically there to help us troubleshoot and triangulate issues, should there be any issues in the systems. So we'll be talking more about these features in later talks and also in the next following presentation for the integration tips. So the news gas connections, if you're wondering what they look like, I have some photos attached in this slide here. Essentially, they're very easy, straight fitted connectors. They have face sealing, face sealing interfaces. So you don't put any sort of, Teflon like you see in the picture here inside the actual threadings, but you just put a sealing surface in between. As you can see there in the picture, there's an O-ring on this fitting. They're widely available from a variety of different manufacturers. So you're not just stuck with swage lock either, but you can actually use whichever fitting type you would like to use. Also enabling people to start welding their fittings in case they wanted to. So this helps us in quite a few ways, but the main thing is maintenance. If you're ever pulling a system in and out of this out of the rack, you would probably have to eventually replace the bulkhead from the tightening and the loosening of the systems or something like this. So these type of fittings will be enabled easily to swap the interfaces. So should any leaks develop on the front panel, you'll be able to swap the systems out easily. Furthermore, they're quite robust. So previously with the nut and ferrule fittings, it's quite easy to damage them during transport or when you're handling them during installation. In this way, it's very, very difficult to actually damage these fittings and interfaces. So if now you're wondering, maybe I should upgrade from the EL2.1 to the 4.0, or my next installation should be 4.0. What do I have to worry about? Well, the main integration rules, they remain unchanged. The bulkheads that were standardized to let you essentially choose how to manage the outputs. But in general, you keep all the hydrogen purges, or the hydrogen vent lines in this case, connected and in parallel. You do the same with the oxygen vent lines. And as always, you would require a water trap to be put inside the bottom of the vent line to manage the condensate from the line. Interfaces have shifted slightly. So if you wanted to replace a cabinet of EL2.1s with EL4.0s, this is not going to be the easiest to do, but it's quite straightforward because you would just have to remake that connections from the cabinet to the front panel of the electrolyzers. But the general, how we can call it, the arrangements of the front panel has stayed pretty static. Oxygen vent, something to consider now that we didn't have before, is due to the catalytic converter on the output of the vent line, the oxygen vent is now heated. So we do not recommend continuing to use these LDPE plastic pipings or tubes on the front panel of the system, because they might have the risk of melting. So fluorinated plastics or metal fittings and metal pipes would be ideal to be used for these systems. Systems that work really well, of course, is something that is good in oxygen environments, even in the worst case scenarios. There's plastics out there that don't really burn. So yeah, furthermore, with the improved diagnostics and sensorics inside the EL4.0, we can actually do better in predictive system maintenance. And yeah, I think this is pretty much it. We got, for installations with multiple electrolyzer versions, it should be noted that the DC-DC versions from the EL2.1 to the 4.0 are compatible, so you can just use the same converter that you used before. But you should avoid to combine the EL2.1 and EL4.0 system vent lines. Simple fact of the matter is the EL2.1 does not have the heat-resistant tubing inside, but the 4.0 does. So you shouldn't mix those two lines, just in case, to avoid any sort of issues there. Okay, now the question is, what does it actually mean ready for integration into an ISO compliant system, and why do you need this? In the end, our system integrators continue to ensure a safe installation with the previous systems, but to deploy these modular low maintenance electrolyzers into what I like to call despecialization of hydrogen production, the system integrators have to continue to take responsibility for safe installation. This can be made a lot easier if you wanted to create an ISO compliant system, because then you have the weight of the industry behind you in terms of deploying, compliant systems. So if you do make a ISO compliant system, this should help you. This should help your integration and deployment efforts, especially for industrial settings. It does increase your design rigor, so there will be some parts and maintenance activities that you will have to adapt to, and that will definitely flow into your system design. And it will also increase the cost slightly, simply due to the adding of the extra parts. But is it really necessary? Not really. Yeah, you can do it, but it's not mandatory. Standards like these, Type C standards, is something that you can achieve whether or not you really need it. Essentially saying that our system is largely ISO compliant, it will already be enough to manage most of the hazards here and to take over the responsibility, because they're clearly defined as to what's still needed to be done. So what do you need to do actually to make the system ISO compliant? It's quite simple, and most of them you have to do regardless. You still have to route the oxygen and hydrogen vent lines outside of the enclosure to a safe area. You have to protect the vent lines from ingress, so no rain, no bugs, no dust, ideally. And you need to enclose the systems in IP-rated enclosures. These ones are for industrial settings, IP22, for residential settings, it'd be IP34, and IP44 for outdoor settings, minimum. And finally, you would have to protect the system from overpressure by installing and maintaining a safety pressure relief device set at 40 bars, which needs to be specified according to ISO 4126-1. This is probably the one that's most critical in this regard, because the safety valves require, depending on local regulations, replacement and frequent maintenance. Yeah, but this is basically the introduction into the 4.0. Right. Questions, I'm sure they came in. So, does Enapter plan to mass produce the EL4.0 at the Germany campus plant? Yes. So production will start from the EL4.0 in Pisa already, but as soon as the Enapter campus is ready, we'll start mass production of the systems there. What will be the operating temperature window for the liquid-cooled version? What is the maximum temperature for the coolant? Good question. I don't think we have the answer for this actually yet. It's going to be bigger than the air-cooled version, but the essential ambient operating conditions have so far been unchanged. We still have to perform the climatic chamber testing for the 4.0, and then we'll be able to give better answers for this. But good question. We'll keep it in mind. Standby power consumption doubled. Why? The reason for this is that we have, the SIL-rated safety functions. They have to be powered at all times, essentially, unless there is a power cut. So essentially, having the active sensoric there will do this. Can the dryer therefore make more electrolyzers? Make sure to run it nicely. I see. To be determined. Right now, we're not changing the specifications for the hydrogen purity on the outlet of the EL4.0 yet, as we're pending some further testing, but we can cautiously optimistic that we'll be able to do something. Okay, is there efficiency difference between the AC and the DC version? Oh, sorry, I don't actually know this. Yeah, I will have to ask. We'll get back to you for this. Thank you for the question.
Can you also, when you repeat the question, maybe take a bit more time to just to repeat it, please?
Sure. Yeah.
Thank you.
No problem. Okay, then Armando Izquierdo is asking us, so how does the EL2.1 detect hydrogen leaks? We don't detect hydrogen leaks in the EL2.1. We detect pressure inconsistencies. So we have constant air dilution in the EL2.1. This is the same safety concept as the EL4.0 actually. However, in the 4.0, we have a hydrogen detection sensor integrated into the control system. And this just helps triangulate and predict problems from, either internal to the electrolyzer or even external. Miguel Sousa is asking, the EL2.1 don't show the specification, but also has 2.4 gigahertz Wi-Fi and Bluetooth, correct? Yes. I'm surprised it doesn't say this. Is the BSPP to swage lock fitting included in the package? I think that decision is still to be determined, but right now it's looking like a yes. It looks physically smaller, but performance is a bit lower. What benefit can I expect from the 4.0 compared to the 2.1? The performance is not lower of the EL4.0 than the EL2.1. The performance is the same, and if anything, while the standstill power might be slightly increased, we are pretty confident that the actual hydrogen output purity is going to be improved slightly. Ulf Jürgensen is asking us, what about the hydrogen output quality? 99.9% as much more water. Does the dry need to be changed? Oh, right. I've addressed this. No, not really. And it's to be determined if we can actually dry more hydrogen with the dryers that we have right now. Right now, we don't have any plans to make a direct new version of the dryers and water tank modules to upgrade them to the 4.0, but this will happen eventually for sure. What is the recommended room temperature around the electrolyzers? How much wasted heat must be removed in an air-cooled and liquid-cooled electrolyzer? Good question, Eduardo. So the recommended room temperature is between 5 to 45 degrees Celsius. Waste heat depends on the point in time of the system. At the end of life, you have to dissipate, I think, about 1 kilowatt of heat from the air-cooled version. But we'll be covering this a little bit more also during the cluster and integration tips topics. Vimal Pandya is asking, considering heat dissipation from the equipment, will the multi-core consist of AC systems? Okay. I think this is not the relevant discussion. The multi-core is not built with the same electrolyzers inside, but it's a different type of build-up. So the cluster itself is the combination of all the electrolyzer modules, and the multi-core is a different type of construction. Which is better for AC or DC for electrolyzers? Joe. One of the Joes is asking if it's better AC or DC. Personally, I prefer the AC version, but there's no right answer there, I think. It depends on the application. If you have questions about which system to deploy in the best way, we're happy to help you out. We can jump on a phone call together. What is the maximum number of EL4.0s in a single site? Good question, Dieter. This is up to you. So at some point, it would stop making sense to integrate single devices, and then it'd be better to go for larger units. But I think it'll make sense to, kind of call it, I don't know. Good question. We'll get back to you about this. What is the temperature of O2 and can we use it as medical O2? Yeah, I would like this to be the case, but for now, no, it cannot be used for medical purposes. Overall, again, part of ISO compliance actually is about kind of restricting the use of the oxygen. So from our side, the oxygen is not ready to be used directly from the electrolyzer without special considerations. Sandeep Kande is asking, is there a limit for connecting 5 systems in a single control? Is there any limit for connecting 5 systems in a single control and water cooled as like 2.1? I don't understand the question, but I think what the question is asking is, how many units can you connect together in the water-cooled loop? As many as you would like. So there's people building cluster installations with 30, 40 electrolyzers, and they're all liquid-cooled. Also for the EL4.0, this will be the case. Do you require a consistent voltage and power of DC supply, or is it possible to use a variable source? You can use a variable source. Which one is better for a new user? I'm assuming you're asking about the AC or DC versions. The AC version is easier. It's more straightforward. I think the DC versions are a bit more complicated. I think several people have been asking, why is the purity of the 4.0 lower? What is the contaminant? So actually the purity is not lower. I apologize for the data sheet in this way. This is a preliminary data sheet, and information on there was subject to change. So I highly suspect that the hydrogen output purity will improve compared to the EL2.1. The contaminant remains the same. It's basically just water. So we don't have any contaminants like you would normally have from steam methane reformed hydrogen. The purity of our hydrogen is really dependent on, I guess, on nothing. It's just always very good. What lifetime do we expect from the 4.0? And can't read this. For the 2.1, it's recommended to install check valve in O2 line. For the EL4.0, you will not need to install a check valve in the O2 vent line anymore. Okay, I think I've kind of gone over my time actually answering questions. If I haven't answered your questions at this point, I think we can get back to you directly via the support team chat, or maybe we'll be answering your questions also later on in different presentations. Good. Thank you, everybody.